This video will discuss energy, free energy, and endergonic and exergonic reactions. Let's start with energy. There are better and more complex definitions of energy, but we'll just go with the simple definition that energy is the capacity to do work. There are many forms that energy can take: light energy, heat energy, electrical energy, mechanical energy, nuclear energy, and chemical energy. And on top of that, we have the concept of potential and kinetic energy. Potential energy is stored energy, while kinetic energy is the energy of motion. So, for example, if we have water held behind a dam, this is potential energy. If the dam were to break, however, the water would begin moving downstream, exhibiting kinetic energy, since now it is in motion. Similarly, molecules have potential energy stored within the bonds that hold atoms together. For example, here are two molecules that have potential chemical energy within those covalent bonds. Do you recognize the molecule on the top? This is glucose, a monosaccharide or simple carbohydrate. What about the molecule on the bottom? This is a fat. Notice the classic triglyceride structure with 3 fatty acids extending from a glycerol backbone. And all of the covalent bonds within these molecules have stored chemical energy. When we break these bonds during the process of cellular respiration, we release that chemical energy. Let's tie this concept to something we already know about in terms of metabolism. Recall catabolic versus anabolic reactions. Catabolic reactions are when we break a larger molecule into smaller molecules, and we've talked before about how they release energy. This is why, because we're breaking the chemical bonds in which energy is stored and releasing that energy. On the other hand, anabolic reactions are when smaller molecules are joined together to form larger molecules. These require energy to be put in because we're forming new chemical bonds. We're going to start using the words exergonic and endergonic to capture this concept of energy being either released or required. Exergonic reactions are those in which energy is released, so catabolic reactions are also exergonic. Endergonic reactions are those in which energy is required for the reaction to proceed. So anabolic reactions are also endergonic. If you're having trouble keeping the words straight, think exergonic, energy is exiting, and for endergonic, energy is entering. We can also express the amount of energy transferred during a reaction as Gibbs free energy. Think of Gibbs free energy as the amount of energy that is available to actually do work. We use the term delta G to refer to the change in free energy during a reaction. We can calculate the change in free energy in a reaction by taking the change in enthalpy minus the change in entropy times temperature. But practically what we're really interested in is a change in sign. In other words, if we think about the reactants and products in a chemical reaction, do the reactants have more energy than the products? In that case, we've released energy and have an exergonic reaction. I like to think about it going downhill as energy is released and the products end up at a lower state of energy than the reactants. Or on the other hand, do the products have more energy than the reactants? In this case, we had to put energy in, we're going uphill, and we have an endergonic reaction. And we can also graph the change in free energy over the course of a chemical reaction. It looks something like this. Let's break it down and start with an exergonic reaction. In an exergonic reaction, the free energy of the products is lower than the free energy of the reactants. You can tell because the products are lower on that y-axis. We're graphing Gibbs free energy on the y-axis and time or course of the reaction on the x-axis. Energy has been released during this process. Therefore, the change in free energy, delta G, is a negative number. It is less than 0. On the other hand, for an endergonic reaction, energy is required. It must have an input of energy to proceed. In this case, our free energy of the reactants is lower than the free energy of the products. So the change in free energy, delta G, is a positive number. It is greater than 0. So endergonic reactions will have a delta G, which is greater than 0. Okay, so when we look at chemical reactions, let's tie these concepts together. Anabolic reactions are reactions in which smaller molecules are assembled into larger ones. These reactions are endergonic, meaning they require energy to be added, and their delta G is greater than 0. On the other hand, catabolic reactions are reactions in which larger molecules are broken down into smaller molecules. Because chemical bonds are being broken, these reactions are exergonic, meaning the energy is released and their delta G is less than 0.